Let's do an example with velocity addition as an example of vector addition. Let's say that an airplane is flying relative to the air at a direction parallel to the ground, 45 degrees north of east. So it's flying at an angle 45 degrees north of east. And let's say it's flying at a speed of 200 meters per second. And now imagine that the plane that's flying in the air itself is moving, the wind is blowing, and the wind is blowing to the east, let's say at 50 meters per second. That's a high wind, but that's okay. So just imagine that relative to the airplane's going 200 meters per second, 45 degrees north of east, yet the air is all moving to the east at 50 meters per second. So the velocity of the airplane relative to the ground is going to be the sum of those two vectors, right? The velocity of the airplane relative to the air is going to be, relative to the air, let's just draw it, is 200 meters per second. But then the air is pushing that pushing that airplane 50 meters per second to the east. 50 meters per second. Not a good scale diagram. Whoops. That should have been a little shorter compared to the 200. So the resultant vector, the sum of those two vectors, the sum of the airplane relative to the air and the air relative to the ground, is going to be the speed of the airplane relative to the ground. I'll draw that. So if we know an airplane can fly 200 meters per second, we know its direction relative to the air is blowing it, so now I just want to find, so what is that resultant velocity relative to the ground? In other words, how long is it going to take to go from Lynchburg to Tulsa, Oklahoma? So let's go ahead and add those two vectors to find this resultant vector, which I think the color is black, I'm not sure. Okay. So to do this sum, I'm just redrew it on a new page. To do the sum, I'm going to take the x and y components and say then the v resultant vector is going to be v1x plus v2x, right? Take the x components, add them together, plus v1y plus v2y. The y components, add them together in the y direction. So I just took a shortcut, right? Because v1 is v1x in the x direction plus v1y in the y direction. v2 is v2x in the x direction and v2y in the y direction. So when I add v1 plus v2, I can add the x components and add the y components. And so now I just have to take the components of each of these two vectors. So in order to take the components of each two vectors, I have to take each vector and put each vector, so its tail is the origin of our coordinate system, right? And I can move the coordinate system so that it's at the tail of each vector to take each of the components. And then I can drop the perpendiculars to the axis and take the components. So drawing the two perpendiculars for v1, I get v1x and v1y. I can do the geometry of that right triangle. And then notice that v2 is along the x-axis, so v2 is the x component. The x component is 50 meters per second in the I direction. Okay, so v1x is equal to 200. Let me just go ahead and think about this. v1x, we can use the cosine of 45 degrees equals v1x divided by 200 meters per second. And we can say that the sine of 45 degrees is opposite over adjacent, so the opposite is v1y over 200 meters per second. So we can use the cosine and the sine to find v1x and v1y, and that's from the geometry of the right triangle. It's not a definition, right? It's just the geometry of the right triangle, SOHCAHTOA, and so from that we can find v1x and v1y, and by plugging into the calculator you find that v1x is equal to v1y, and they're both 141 meters per second. Remember, v2x is 50 meters per second. And what's v2y? v2y is 0 because v2 is all in the x direction. So now we'll go ahead to the next page and write out our actual vector sum. So the v1 is 141 meters per second I plus 141 meters per second j. Whoops, I forgot the units. Meters per second. And v2 is 50 meters per second I. The resultant is the sum of the x components in the I direction plus the sum of the y components in the j direction. So therefore the resultant, or the sum, right? That's the sum vector, the resultant vector. I just called it the resultant vector this time. But it's the sum of v1 and v2. The resultant is equal to, resultant is equal to 191 meters per second in the x direction plus 141 meters per second in the y direction. So that's the resultant in component form. What about in magnitude direction form? What is the net magnitude of the airplane's speed relative to the ground, and what is the direction of the airplane relative to the ground, right? Relative to the air, it's 200 meters per second, 45 degrees north of east, but relative to the ground, it's being blown to the east more, it's going to be slightly different. So let's go ahead and figure out the magnitude of the resultant vector. V resultant magnitude is, using the Pythagorean theorem, is going to be the square root of 191 meters per second squared plus 141 meters per second squared, using the Pythagorean theorem. And the angle, we can say that the tangent of theta, if we draw the resultant vector, I just drew a little picture in the corner there to show that the tangent of theta is Vy over Vx, and so therefore theta is the inverse tangent of Vy over Vx, which is 141 over 191. The units cancel. And so that's our answer. We can now plug those two into the calculator just to find the numerical result. So plugging it into the calculator, the numerical result is 237 meters per second is the magnitude, and the direction is 36 degrees north of east. How do I know it's north of east? It's because it's this vector here, and that the angle we were measuring was north of east, 36 degrees north of east. Okay. That's the answer.